In this lecture, we are going to talk about two terms which are very often used in connection with oscillators and frequency synthesizers. So these are phase noise and jitter. So these parameters are used to characterize purity of any signal which is periodic. So we know that oscillators and frequency synthesizers or even PLLs, they basically produce periodic waveform. And in real life, none of the periodic signals are going to be very pure. That means they are not going to have ideally constant period for every cycle. So here we are going to use these two parameters to talk about the non-idealities of the periodic signal. So if we have an oscillator or PLL, and if this is ideal, then we will have output voltage VOT, and this is going to be periodic. And say, for example, it is sinusoidal. So it will be given by this expression where we know that this is called phase of this periodic signal. And the frequency omega naught is going to be derivative of this phase, and this will be equal to 2 pi by T naught, where T naught is period of the output. That means VO. Right. So VO is A sine omega naught T or A sine 2 pi T by T naught. So here if we see the plot of this waveform, then we are going to have this kind of scenario. Yeah. So here we have shown two periods, and each of the cycles are going to be exactly T naught duration. Or to be more specific, uh, it is going to take T naught amount of time to cover this 2 pi phase. And since we know that these waveforms are produced because of a phasor rotating with angular velocity omega naught, and one period is basically the amount of time that it will take to complete one complete revolution. So if we have ideal, then it will always cover this 2 pi phase in T naught duration. And we say that omega naught is constant. And this will happen whenever this is fixed. And if you see the spectrum of this signal, that means if you see the signal in frequency domain, then we are going to have this kind of spectrum. That means there will be an pulse at omega naught. However, in reality, what will happen is that this phasor is not going to take T naught amount of time to complete one revolution. Right. So here, what happens is that in practical cases, the amount of time taken to complete one revolution is going to be slightly different from T naught. Or in fact, each revolution so each revolution will be completed in Ti duration, where Ti will be slightly different from the ideal T naught duration required. So what will happen in this case, if you see the plot of the sinusoid, then in this case, this plot, they are not going to be are of same duration T0. Some of them will be more than T0, some of them could be smaller than T0, like this. So here we have T1 duration for first cycle, then we have T2 duration for the second cycle, and T3 duration for the third, so on and so forth. And as was pointed out, each of these Ti are going to be, so each of these Ti are going to follow this relation, where this delta Ti is going to be typically small. Most of the time, it is going to be quite small. So this happens. That means each revolution is completed in duration different from T naught. That implies that omega naught is no longer constant. That means omega naught is no longer constant and independent of time. So omega naught will now be time dependent, but the deviation of omega naught from the ideal case is going to be small. So since omega naught is not constant, so we can say that this phase is no longer equal to this. So we get this relation only when omega naught is constant. So since now the new omega is not constant, so when we find it out by differentiating this, so here theta or the phase is also no longer going to be. So here we have linear relation and this is going to be non-linear and of course dependent upon t. So this will then give rise to a constant term which was earlier present, and then there will be another term which will be responsible for the change in the phase with time. So here we can then find out eta t as integral of this omega, and this will turn out to be omega naught t plus pi m t. So such type of waveform then can be represented in this form. And here this function is going to be random and typically small. And this function is called phase noise. So here we saw that the non-idealities in terms of period of the each of the cycle of this periodic waveform manifest in terms of time, but this aspect is labeled as phase noise here because we can see that if we have a randomly varying term appearing in the phase of periodic waveform, then that will lead to non-uniformity in the period of the each cycle. So that is why that phenomena which we saw in the time domain is conveyed using phase noise. Now, what will be the consequence of this non-ideality on the spectrum? So if we see the spectrum of this practical or real life periodic waveform, then this is going to be like this. So we will of course have omega naught component, but then there will be other frequency components also present in the neighborhood of omega naught. So we see that we no longer have a pure sinusoid present here. And we can get some idea that why it should be something like this from this expression. So here, when we expand that expression, let us say this is equation number 1. So here we find that this phi n is randomly varying but small quantity. So this cos phi n is going to be approximately 1. So we can now approximate this relation a sine omega naught t. So this will be approximated to 1. And here, since this is very small, so we can approximate this sine term as a phi n t. So what this says that if we try to find out the power spectrum density of this, so it will contain an impulse. That means it will contain this pure sine wave, which is present here. And then it will contain the power spectrum density of this phi n shifted to omega naught. And the power spectrum density of this phi n is responsible for widening of this profile. So how do we specify this phase noise of uh, practical or real life sinusoid signal? So what we do here is that we take certain offset from this center, say delta f, and at this offset in 1 hertz bandwidth, we measure what is the power. And then we also measure the power of the carrier. So this is the power of the carrier, and this is the power in 1 hertz bandwidth at a certain offset given by delta f. So how this phase noise is specified or measured? So this is found as 10 log of this power at delta f in 1 hertz bandwidth, say in milliwatt, and then divided by power of the carrier also in milliwatt. Yeah. So here we see that the power at offset is being normalized with respect to power of the carrier. And since we have taken this quantity in log, so the unit is going to be dB. So we are basically talking about the ratio of the two power, but the second power, the power with respect to which the power in the offset is being specified is of the carrier. So that is why we say that its unit is going to be dBc. So dB with respect to carrier, and for the numerator we calculated the power in 1 hertz bandwidth. So we also convey this information by saying that this is power relative to carrier but in 1 hertz bandwidth. So unit of this phase noise is dBc per hertz. So this is how we will calculate if we have the absolute power in milliwatt. Now this can also be calculated if we have the information of the power of each of these two cases in dBm. So this will become 10 log power at delta F in 1 hertz bandwidth in milliwatt minus 10 log power of the carrier also in milliwatt. So we see that the first term is basically the power in milliwatt. And keep in mind that this quantity is for 1 hertz minus power of the carrier also in dBm. And this is in 1 hertz. So this can be calculated directly from the PSD plot because this will be typically in dBm. So we just measure this value, we read this value, and then subtract that value from the value that we have obtained from uh, calculating the power in 1 hertz bandwidth at delta F. So this is how we can calculate this thing in real life. So this was about the non-ideality of a periodic waveform, typically sinusoid, in terms of frequency. So here what we have done is that non-idealities have been described in terms of frequency domain. But the non-idealities, they can also be talked about in time domain. So when we talk about time domain, we typically use term jitter. So for talking about this jitter, we typically use the square wave, but this can also be talked for the sinusoid signals. So jitter is time domain characterization of uh, square wave, say a clock in yes, of a square wave which has non-uniform period. In fact, all the real life clock will have this property. So in real life, we will always have this kind of clock. So here see that the period of every cycle is deviated from the ideal period. So this is the ideal period. But period of every cycle is different from that value. Could be slightly less or slightly more than that one. So here also each TI is going to be deviated from the ideal case by typically a small amount. But unlike the phase noise aspect, this need not be always random. So whenever we use a clock like this, we always want a period to be exactly equal to same value, because everything in the clock driven system will occur either as the rising edge or that falling edge. So if these two edges are occurring either early or after the ideal case, then there will be issue in the system. And this deviation of the period from the or the falling or rising edge from the ideal location could be either because of the uh, random phenomena, or it could be because of a deterministic signal. So whatever may be the case, this deviation is always unwanted, and this will be always described by jitter. So here this could be either random or deterministic. So this is one key difference between parameter uh, phase noise and jitter. Now this jitter, they are characterized in various ways, unlike the phase noise where we had a very well-known way of talking about it. So here this is characterized in a number of ways. We will go through all those ways. So each of the ways definitely conveys the non-idealities or the deviation of the period from the uh, ideal case. So the first way in which we talk about jitter is called absolute jitter. So this is calculated with respect to an ideal clock. So we have, say for example, an ideal clock and then a practical clock where the time periods are different. Like this. So here each of these cycles, they have exactly same period T naught, but here the periods are different. So what we do in the absolute jitter way of specifying this non-ideality is that we measure the deviation of the rising edge of the practical clock with respect to the rising edge of the ideal clock. So gap between the rising edge of two clocks are noted down. Say the rising edge of practical clock occurs at T0, and then at T1, then at T2. So these are the moment when the rising edge of the practical clock occurs. And we measure this gap, and this is what is called as the absolute jitter. So these gaps so absolute jitter difference between the rising edges of ideal clock and practical clock. So this quantity will be designated by JAN, and this is going to be equal to, say, the rising edge moment of the nth clock minus duration of n cycle. So ideal clock rising edge will occur at this moment, but for the practical clock, the rising edge of the nth cycle will occur at this moment. And here, this is typically going to be small, but not always. And this could be random or deterministic. So depending upon what is the nature of this jitter. So here we have defined these non-idealities of practical clock with respect to ideal clock. But in real life, unfortunately, we will never have this ideal clock. So this technique cannot be used in real life to characterize any practical clock. So we are now going to talk about uh, different way of talking about this jitter without the help of ideal clock. So this is called relative jitter. Instead of comparing the location of the rising edge of practical with respect to that of ideal, what we do is we take this wave also as the another clock, which is supposed to have, of course, the same frequency. So we take two non-ideal clocks and then compare the difference in the rising edges of each of those two clocks. So this relative jitter is difference between the rising edges of two practical, that means non-ideal clocks. So we have one clock which is non-ideal, and then we have another clock, and this is also non-ideal. So now we measure the gap between the rising edge of these two clocks. So this relative jitter, this is calculated as find the rising edge of nth cycle of clock 1, and then from it subtract the rising edge location of clock 2. So say this is T0 clock 1, this is T1 clock 1, this is T2 clock 1, and this is T0 clock 2, this is T1 clock 2, and this one is T3 for clock 2, so on and so forth. So this is how we calculate relative jitter. But this jitter can also be expressed in terms of absolute jitter. So what we can do is we can add and subtract n into T naught. So where T naught is the uh, expected period of those two clocks. Or if we had an ideal clock, then T naught would have been the period for each cycle. So now we can rearrange them. So now we see that this first term is the absolute jitter for the clock 1. And this second term, this is absolute jitter for clock 2. So relative jitter, this can also be specified in terms of the absolute jitter. Third way of specifying this jitter is period jitter, or this is also called cycle jitter. This one is specified as difference in the period of one non-ideal clock. Say we have here period of non-ideal clock as say T1, T2, and so on and so forth. So this period jitter is specified as difference between these periods and the period of the ideal clock. Or this can be calculated as the difference between the rising age of two cycles. First, we calculate the period of one cycle. Say we take n plus 1th rising age and from it subtract the nth rising age. So this will give the period. We can call it the nth period also. So now we see that what is the difference between this period and the ideal period. So periodic jitter is calculated as period of non-ideal clock minus the period of ideal clock. So this will give also the idea of how much deviation of the non-ideal clock cycle occurs with respect to the ideal clock. And this can also be specified in terms of absolute jitter. So we can do the manipulation. Tn plus 1 minus Tn minus T0 minus n T0 plus n T0. So here we can combine and write n plus 1 T0 plus n T0. Now this term and this term, they can be combined. And similarly, this one and this one can be combined. Now we see that each of these two terms, they are basically the absolute jitter. So this period jitter is equal to absolute jitter for n plus 1th cycle minus absolute jitter for nth cycle. So here what we have done is find out the difference between the time period of one cycle with respect to the ideal clock. But sometime, for example, in the case of divider or counter, we are interested in knowing what is the deviation of the final clock age with respect to the ideal uh, divider. In those cases, we do not try to find out the difference between one period of the non-ideal with respect to the ideal. Rather, we try to find out the difference in the duration of n cycle of non-ideal with respect to n cycle of the ideal case. So we define a slightly modified version of this period jitter as n period jitter, and this is also called accumulation jitter because we are talking about the deviation of n cycles of non-ideal waveform from the ideal case. So this is difference between n consecutive. So we take n consecutive cycles of non-ideal clock and then find out its difference with respect to that of the ideal clock, for which duration is going to be n t naught. So rising age of n consecutive clocks is going to occur at this moment, and this will be with respect to the nth clock. So after n clock, we wait for additional capital N number of clocks and find out the difference, and then this difference is then compared with the duration of the n cycles of ideal clock. And this can also be again converted into in terms of the absolute jitter. So here we have Tn plus n minus Tn minus n T naught. So minus n T naught plus small n T naught. So here we can combine these two terms. Now these two can be combined together. So here this can be written in terms of absolute jitter. So this is absolute jitter for n plus nth minus JAN. Okay. And the fifth way in which we specify this jitter is called cycle to cycle jitter. So here what we do is we find out the difference between the two consecutive periods. So this is one period, and then we have another period here. So they are not going to be equal. So when we specify this non-idealities in terms of difference between these two, this is called cycle to cycle jitter. So this will be represented as, so say we take n plus 1th period, and from it we subtract the period of the previous cycle. So this is difference between period of two consecutive cycles. So this is how we talk about the non-idealities in terms of jitter and phase noise. As was pointed out, this jitter can be deterministic and random both, but phase noise is always random. So we can take one example of deterministic jitter. Say we have an VCO whose output is modulated or whose control voltage is being determined by a sinusoidal waveform, say B cos omega mt. So we know that this output, which is going to be a sine theta t. So now this theta t will be dictated by this input voltage, control voltage. So we know that theta t is given by omega naught t plus a VCO integral of Vi. So this is how the output frequency or the phase of the output of VCO is going to be determined. So this will be omega naught t plus k VCO. From here we can calculate this. So in this case, the output is going to be sine omega naught t plus k VCO divided by omega m b sine omega m t. So here we see that we have this form which we pointed out earlier. So in this case, this phi n is no longer random. This is a deterministic signal. So this is a not random, whether it is deterministic. However, this will definitely give rise to non-uniformity in the period. All periods are no longer going to be same equal to ideal period of uh, T naught. Which we would have got for omega naught frequency. But in this case, since this non-ideality is given by deterministic signal, so this is a deterministic jitter. So this will lead to deterministic jitter. While for phase noise, this should be random. Now, if we see the spectrum of this signal, then what we are going to get? So if we see the spectrum of this, so if we expand this, we are going to get form which we have already derived for this case, and for that case we found it was a sine omega naught t plus a phi n cos omega naught t. So this is what we had got when we carried out derivation with phi for small, of course, small phi n. So here we get this term, and now this is p not B, but in fact there will be constant here. So let us say C, where C is equal to this factor. So this is C. So here we see that ultimately we get three terms. Right? So we see that the three frequency components in the PSD are present. Omega naught plus omega m and omega m minus omega naught. So if you see the PSD, for this case, we are going to have this omega naught and then omega m minus omega naught and then omega m plus omega naught. And the values of these or the strength or the power of these are going to be small. If we have a small value for this, which we have to assume, then only we will be able to arrive at this expression. So this is based on fact that this one is small. And that will be small because C will be small. So C being small means this factor KVCO B divided by omega m. So here we see that as the omega m rises, that factor is going to be small, and then we will have this kind of response. So here these two additional outputs, they are called spurs. So they are the spurious periodic waveform which is present in the output, and this one is the ideal desired. So we see that output, and this is also called shaping of noise by an oscillator. So keep in mind that PLL and frequency synthesizer, they basically contain this VCO. So this one has some relation with the consequence of the noise in PLL also. So we know that using feedback model, an oscillator is presented in this form. And typically this input will not be present here. But suppose we have a noisy input which is being injected here. Then we want to know that what will be the uh, output with respect to this noisy input. So here we are going to find out the transfer function. So we know that this transfer function we had already derived. This one will be of form A divided by 1 minus beta A, where in general all these are going to be frequency dependent. And at oscillation, we know that beta A is equal to 1. So we see that the phase of beta A is going to be 0 or 360 degree. Now using Taylor's series, we can expand this factor. So why we are doing is we are basically trying to find out what will be the value of this transfer function in the neighborhood of omega naught. So suppose this oscillation occurs at frequency omega naught. So we want to know that what will be the transfer function value when we are slightly away from omega naught. So we basically want to know here. So at this value, we want to know what will be the this transfer function. So we will carry out the Taylor series expansion of this beta A. So we will have second and higher order terms here. So since we are interested in finding out the value of the transfer function for very small or small offset from the center frequency, so these are going to be small and they can be neglected. So this beta A at slight offset is approximately equal to beta A g omega naught plus delta omega d beta A by d omega. So this is the approximate value. Now at oscillation, we know that beta A j omega naught is equal to 1. So we can now write this beta A j omega naught plus delta omega is equal to 1 plus delta omega d beta A by d omega. So this is 1 minus beta A is equal to delta omega d beta A by d omega. So now we can use this one. Say this is, let us first call this as equation 2. So 2 can be modified with the help of 3. From 3, 2 becomes going to be So this is what we are going to get here. And this relation, this also implies that beta j omega naught a j omega naught is equal to 1 implies that a j omega naught is 1 by beta j omega naught. So therefore, this 4 implies mu by Vn is equal to 1 by beta j omega naught. So here this term is approximated to a j omega naught plus j delta omega. So we get this expression. So now we need to find out what will be this expression. So for that, we will represent this beta A in the polar form in this way. So therefore, derivative can be written as so when we try to find out the square of this or the magnitude of this, this will give rise to so here we see that this term is equal to 1 at the oscillation, and this beta A is going to be high. So if we make a plot of this magnitude and phase of this beta A for an oscillator, so its plot will typically be like this. So this is the oscillation frequency, and at oscillation frequency we see that the phase is 0, so phase will typically undergo transition at this omega naught. So this is the typical behavior of beta A at and around omega naught. So here we see that beta A is equal to 1, the fact which we have been knowing, and not only that, we also see that this plot is going to be quite flat. The slope is going to be very less around omega naught. But here if we see the phase, then the slope is going to be the highest at omega naught. So the rate of change of the phase of beta A around omega naught is going to be significantly large. However, the rate of change of magnitude of beta A is going to be very less at around omega naught. So this says that this term is going to be approximately equal to 0, very small, and this is anyway equal to 1. So only this term will survive here. So the magnitude or the square of the magnitude of beta A derivative with respect to omega is going to be approximately equal to square of the rate of change of the phase with respect to frequency. And there could be a scenario when we have a sharper peak like this. So usually the more sharp the peak, the more steep transition of this phase is going to happen. So this sharpness of this oscillation is conveyed by a parameter called quality factor. So an oscillator is characterized by quality factor, and this parameter is related with the rate of change of phase. So we see that the sharper this peak or the oscillation, the faster will be the phase change around the oscillation frequency. And this is then multiplied by this factor oscillation frequency. So using this, we can rewrite this derivative square of the derivative term. So therefore, d beta A by d omega magnitude square, it basically becomes equal to omega naught q 2q by omega naught square. So here we have substituted this in terms of quality factor. So therefore, we can rewrite this square of the transfer function in fact, here we had already written it. So square is given by this factor. Now we can find out what will be the transfer function. So here we found that transfer function has this derivative, which we have found out in terms of quality factor. So now we are going to write the square of this transfer function. So using this equation 5, we can rewrite this factor. So this becomes 1 by beta square, 1 by delta omega square into 4 q square omega naught whole square. So this one will be the magnitude of the transfer function of the oscillator. So here we see that this is going to depend inversely on the square of delta omega. So as we move away from the center omega naught, the value is going to degrade very fast with the square of the offset frequency. So here what is going to be the consequence, that if we have an oscillator and if we are feeding a noise with say power spectral density as that of a white noise, then this output is going to have a power spectral density of this form. We say that the oscillator is basically shaping the power spectral density of the noise. And this profile here, you can see that this will be dictated by delta omega square.